So it's time to start. So today's speaker is Jenke van der Laag from the Leiden Observatory in Netherlands. So let me introduce her history part. She took her PhD in Leiden Observatory, and after that she moved to Hawaii and Canada, worked as a postdoc. And from 2021, she came back to the Leiden Observatory, and she's now working as an assistant professor. So she's talking about the novel views on planet formation and that evolution. I think it is a very interesting topic between the exoplanet and planet formation. So, okay, so let's start the thing.
Thank you very much. And yeah, thanks for the kind invitation. I'm happy to talk today about essentially the research I've done on protoplanetary disks and all my observations and the connections that I found with exoplanet demographics and how they then link to planets, hopefully link to planet formation models. So this is where I really would like to talk to you guys this afternoon. So yeah, okay. It went so well before. It went really well before. I think it's a bit sensitive to direction. Okay. Well, otherwise I just have to stand here. Now it works. Okay, cool. So one of the main motivators of this work is, of course, the enormous number of exoplanets that have been discovered so far. The counter, I used to look up the exact number, but now I'm just saying, okay, it's more than 5,000. And eventually I will update that to more than 6,000. And one of the things that we have noticed in the exoplanets population is that there are so many exoplanets that are completely different from the planets in our solar system. So here I've just indicated a couple of the major populations. So we have the hot Jupiters, the gas giants, the white orbit giants, and the super Earths. And then the solar system is kind of an outlier in all of that. This is partially sensitivity related, like we're not really sensitive to many of the planets, but there's definitely populations of planets that we don't have. And that means that if we want to build a planet formation model, we need to build towards the full exoplanet population and not just the solar system. So planet formation, we generally visualize through this sequence of events. We need to grow tiny micrometer dust grains to pebbles, continuing to grow to rocks, planetesimals, and cores until we're left with either a rocky planet. And then if at that point there's still gas present, you can actually accrete gas as well, forming gas giants. In combination with migration and scattering events, you will then end up with a planet population that we are observing today in the exoplanet demographics. So the major problem of connecting observables with the planet formation picture is that only the first steps of grain growth and the final results are directly observable. So we can say something about grain growth in disk, and we can say something about the final exoplanets. But all the steps here in between are essentially constrained by theory. Luckily, they do depend on a lot of parameters that we can derive from protoplanetary disks. So this is kind of where our fields meet each other. So in protoplanetary disk studies, we can derive disk masses, timescales, radial scales, trends with various properties, and then occurrence rates in the exoplanet population. So these are kind of the tools that we are trying to provide so that the planet formation models can do their job properly. So to take a step back, the standard model of star and planet formation, which is essentially star formation and disk formation, is shown in this graphic. So this starts with the gravitational collapse of a molecular cloud into a prestellar core that eventually turns into an embedded protostar. At this stage, disk will fall in through an accretion disk, and the envelope material is being pushed away by the jets originating from the protostar. All of this happens in sort of the first million years. After the envelope is gone, we typically talk about a protoplanetary disk or a planet-forming disk, which will live several million years. And after the disk is gone, we can talk about a planetary system, sometimes also with a debris disk. the ALMA telescope has of course really revolutionized the field of protoplanetary disks. So I just want to show one of these nice galleries of ALMA protoplanetary disk observations. I hope several of these images are familiar to you, like for example the HL tau image with the very narrow gaps, but also several of these what we call transition disks, the disk with the large inner cavities, and also the asymmetric disks. Overall, the ALMA millimeter observations of disk have shown a very large diversity of substructures at fairly large scale, 10 to even 100 AU in radius. That's where we can find and actually resolve these substructures. So in order to understand, like, where do these substructures come from, what is the origin of the dust rings and the asymmetries, we actually need to go back to the very old picture of protoplanetary disks. So this was already figured out in the 70s, that if you have a smooth disk of gas and dust with the star in the middle, the gas disk will have a pressure gradient. And as a result of that, the gas itself and also the small grains that are coupled to the gas will move sub-Keplerian. So they will move a little bit slower than Keplerian orbits. However, the small grains will start to clump together to larger sizes. And as soon as you're at let's say a millimeter size in the outer disk, the grain starts to decouple from the gas, and therefore it will no longer feel this pressure gradient. So it wants to move Keplerian. It's no longer limited by this gradient, but it is surrounded by all this material that is moving a little bit slower. So as a result of that, it experiences a headwind and drifts inwards towards the star. So a large dust particle moves in the direction of the highest pressure, which is in this case the center of the disk, and then even the star. So what this already tells us that the dust disk will actually evolve differently from the gas disk. Like, the dust will grow and drift through these processes. At the same time, this radial drift phenomenon was identified as a problem for planet formation, because if you grow grains to larger sizes and then they immediately drift inwards, you will never have the time to form planets out of these grains. So it was proposed that you need pressure bumps, so local pressure maxima in the outer part of the disk, in order to prevent this radial drift from happening. So one of the ideas for that was essentially, if you form first planets somehow, the planet will carve a gap in the gas distribution, and at the outer edge of that gap, you will naturally get a pressure bump where the dust will get trapped. Like, it moves inwards from the outer disk, and then over here there's the opposite pressure gradient, so it cannot drift further inwards. So in this way you would get a ring, and in the simulation here on the right, we see kind of an additional effect that could happen in one of these radial pressure bumps. It's called a Rossby wave instability, and that results in large-scale vortices, again at the outer edge of such a planet gap. And such a large-scale vortex is essentially an azimuthal dust trap. So that will result in these asymmetries that we see in some of these ALMA disks. Yeah. Mm-hmm. Mm-hmm. So let's have a planet. Yeah. You wanted to collect that to create a planet. So yes, that's my next slide. Here we go. We haven't solved that problem. It's yeah, there's clearly a chicken and egg problem, and I was kind of hinting at that already. We need a planet somehow. We need to form the first planet somehow, and as soon as we've done that, we can form more planets. But we don't know what came first. So this is chicken and egg. I'm not going to provide the answer in this talk, unfortunately, because we still don't have it. So we're just going to talk about dust traps as a phenomenon that is caused by planets, without wondering how that first planet formed. But if you guys know the answer, I would love to hear it. Okay, so how do we recognize these dust traps? Because it's not actually enough to see substructure. The way that dust traps were really confirmed was by comparing the distribution of the large dust grains observed by ALMA with the distribution of the gas, for example, through 13CO molecular line emission, and also small dust grains, which we can trace in near and mid-infrared. So here we see two examples, one of radial trapping. So we see that the gas and small dust, they show rings, but the millimeter dust shows a much narrower ring that is further out. So the dust grains are really concentrated at the outer edge of the gap that is carved in the gas. And in the case of Iris 48, we see we can recognize this segregation even better because the millimeter grains are concentrated in this azimuthal dust trap, while the gas and the small grains are still showing a full ring. So it's really this segregation of millimeter dust and gas small grains that is evidence for trapping. Well, coming back to the chicken and egg problem, why do we really think that these dust traps are caused by planets? There has been a lot of debate about this for many years, but luckily by now we have two very firm detections of protoplanets in two of these disks with gaps, so the PDS-70 system and also the ABR-Righe system. So in both cases, the planet has been observed in multiple observations, multiple epoch analysis has been done. There is really a blob that moves at the right orbit. So these protoplanets are real. In many other systems, we don't have this direct evidence yet for the protoplanets. We do have indirect evidence, for example, circumplanetary disk. Well, of course, one in PDS-70, but also one here in AS209. We do measure these deep gas gaps. So that's also, in a way, evidence that, yeah, something must have carved the gap. And then even more indirect spiral arms and also non-Keplerian motion in the line cubes of ALMA observations. So we do see more and more evidence that protoplanets are present in every single gap. Yeah. Sorry, a line cube is molecular lines that we can observe with ALMA. We observe at every velocity. Essentially, we can separate the signal at all the different velocities of the disk. And this is one channel in that line cube. I'm not going to show too much of this, but I can show you some more examples this afternoon if you want. Yeah. So it's essentially non-Keplerian motion that we're tracing. Yeah. Then this is a somewhat more recent result as a piece of evidence for these protoplanets. So in a study by former PhD student Logan in Canada, he showed that many of these transition disks actually have a central emission component in the millimeter, in the ALMA millimeter. And we interpreted this as an inner dust disk. So essentially a model where, a planet carves a gap, but some dust is still flowing through the gap, maintaining the accretion rates, and also creating this inner dust disk. So this seems to be consistent with planet clearing. However, I have been working with a master student and PhD student in Leiden, so Alessia and Jurian, on a multi-wavelength analysis of several of these inner disks. So this is pretty new data, pretty new results. We've shown, well, this is an example of multiple wavelengths or different frequencies of the same disk, where we measure the flux in the inner disk and in the outer disk. And if we then plot them in an SED, so essentially measuring the spectral slope of the outer disk and the inner disk, we immediately see that the slope for the outer disk is much steeper. Essentially, this slope is consistent with thermal dust emission, the kind of value that you expect for thermal dust. Well, for the inner disk, the slope is really flat, which would actually be consistent with free emission, maybe originating from a jet. So essentially, what we're concluding now is that central emission, it isn't large dust grains at all. So the idea now is, yeah, maybe this can tell us something about what's happening in the inner disk. Maybe there's no grain growth, maybe there's very efficient grain growth. And maybe this also says something about the amount of grains that are going through the gap and also onto the giant planet. So I think that this new piece of insight will provide us further constraints on the giant planet formation. Okay, so to come back to the previous part of my story, You may have gotten the impression that rings and gaps are everywhere. Like every single ALMA paper that has been shown in the past few years has shown rings and gaps. And if we think that all these gaps are caused by planets, by giant planets, we have an issue. Because first of all, the giant planets are located, the gaps are located at large orbital radii. And direct imaging has shown us that at least these very massive planets, like superjovians, are really rare. There's only a few % of them at large orbital radii. And even if we go to smaller radii, basically 0.1 to 20 AU, traced from radial velocity surveys, but the peak is around 3 AU, even there, the percentage is like on the order of 10%. So if we say that all disks have gaps and gaps are caused by giant planets, there is a mismatch here. Like there are not enough exoplanets to explain all of these disks. So the reason, or actually the problem in this reasoning is that there in the protoplanetary disk community, there's a very strong bias towards the brightest disks in high resolution observations. So many of the high resolution observations were targeting the brightest disk, not really bothering with the fainter disks. So we're kind of extrapolating that, oh, the fainter disks probably all have gaps as well. But if you want to compare with exoplanet statistics, you need to know what is the bigger picture. Luckily, we do have low resolution observations of full disk populations. So there are these so-called snapshot surveys. You may have seen them in previous talks, where they took observations of 1 or 2 minutes per source, imaging hundreds of disks in nearby star-forming region, but with a resolution of sort of 30, 40 AU, 25, 30 AU. So you can see in the images that many of these disks are unresolved. Some of them show large-scale gaps, but mostly these disk surveys provide us with disk fluxes, disk dust continuum fluxes, which we can convert to disk dust masses. And with that, we can now do some statistics. So one of the results of these surveys was that we can trace disk evolution. So if we look at the cumulative dust mass diagram, we see that the disks in the younger regions have much higher dust masses than the disks in the older regions at sort of 5 to 10 million years. So the disk dust mass decreases with age. Also, we can compare the disk dust mass with the stellar mass. And it turns out that those two parameters are correlated in every region. So here we see all the different regions. And the slope of that correlation steepens over time. So essentially, the disk dust mass scales with the stellar mass, and the decrease of dust mass is primarily present for the lowest mass stars. And then we can set some constraints on the disk dust sizes. So this is a little bit harder because of the low resolution, but there are some constraints, and overall there seems to be a trend that the disk dust size scales with dust mass, and also decreases with time. So this would be consistent with radial drift, right? But it's weird because we were saying like, oh, but there are rings and gaps everywhere. So this is this bias. We think that there are rings and gaps everywhere, but this is actually the bigger picture. Majority of the disks probably don't have gaps. So a little bit more about disk evolution. So if we don't look at the dust, but actually the gas evolution, we have a very different picture of how the disk evolves. There's some debate about the viscous disk model versus the MHD wind-driven model. But both models essentially result in the gas disk accreting its material onto the star, slowly losing their mass, until at some point the accretion rate drops below the photoevaporative rate of the star, and then you very quickly clear the disk from the inside out. So this is talking about the gas disk. And this disk evolution process has been quantified actually quite some time ago by looking at the number of disks, so young stars with infrared access, and also the number of accreting stars as a function of age. And based on these two studies, the typical disk lifetime of the gas and like the small grains was estimated to be about 3 million years. However, if we now combine these two parameters, so we have the accretion rates and we have the disk dust masses, sorry. If we put them in the same plot and actually compare clusters of different ages, first of all, there's a very large scatter in the accretion rates, but also that scatter doesn't become smaller over time. And essentially the scatter is the same for the young region as for the old region. So this suggests that the accretion rate is maybe not decreasing that rapidly over time, even though the dust mass is. So maybe these two parameters are tracing completely different processes, which makes sense because we have dust evolution, we have disk evolution. But I do want to emphasize this point. Well, then in dust evolution itself, we essentially have two options. If we don't have pressure bumps in the disk, we expect all the dust grains to drift inwards. So the evolution will essentially look like this. So this is dust grain distribution as function of radius. But after 3 million years, we see that a lot of the dust is simply gone. And we can also see that in this plot, the dust mass kind of builds up in the first million years, and then it drops very rapidly because of the radial drift. So this is what you would expect for a drift disk. And then for a disk that has a dust trap, you're building up your dust mass, but then because the dust is trapped and doesn't drift further inwards, it remains the same. And this is the cool thing. This is actually something you can see directly if you look at the images of these large disk surveys. So here we're looking at the images of a young region and an old region. And just as a few examples, you see here that the disks that have large scale gaps, they're kind of similar in brightness to the rest of the disk. However, if you look at the older region, the disks that have gaps are much brighter and bigger than the remainder of the disks. So it looks like the disks with gaps are outliers, where the majority of the disks actually become very small. So in order to quantify this and actually answer this question, like how many disks are actually drift dominated or trap dominated, I collected data for a disk survey across all regions. So I gathered all these ALMA data. In the end, I had more than 700 disks within 300 parsec over sort of A0 to M6 spectral types. And for each of these disks, I would measure the dust mass, the disk dust size, but most importantly, I would classify the morphology of each of these disks. So we have the transition disk with large cavities. We have the ring disks with narrow gaps, but not a large inner cavity. And then we have compact disks where there are no gaps present. Well, unfortunately, we have a fourth category. So these, which we call the extended disks. So these are the disks that don't show gaps, but they've been observed at too low resolution to say if the gaps are there. So here we make an informative, empirical argument. If a disk is large, but low resolution, there must be dust traps present because otherwise the dust would have drifted inward. So this is a small fraction of the total disk population, but it makes sense. Like if you look at this disk, it was first observed at 0.3 arcseconds, you see it just looks rather smooth. But then if we observe it at 0.04 arcsecond, you suddenly see that large scale ring. So we're kind of making the same assumption for many of these other large disk which do not show gaps yet. So with these four classifications, we're now going to take a look at the evolution. So we have histograms of young regions, intermediate and old regions. And then we show how many, what the occurrence rate is of different dust masses. The colors indicates the classification of the disk. So the transition and ring disks and also the extended disk are shown in color. The rest, compact disks that are less than 40 AU in size, are shown in black. What you see is that in the young regions, the disk with gaps, they are on the outer ends of the dust mass distribution. They're the most massive disk in the distribution, but they kind of blend in, right? We also saw that in the gallery. However, if you go to the older regions, you see that those gap disks still have similar dust masses, but the majority of the disks have decreased in dust mass. So what we're and actually overall only 10 to 16% of the disks has gaps. So what we're proposing is that there are really true separate evolutionary pathways. The gap disk and the compact disk, where the gap disks are the minority of the total disk mass population. And this also follows from a study by Johan Appegen in Lund, Copenhagen. So the paper was just resubmitted, so I expect it to be on arXiv pretty soon. So he shows, again, this cumulative dust mass diagram. This is from the observations. He can match that with radial drift models, assuming that 5 to 10% of the disks have dust traps. So the majority of the disks will be drift dominated according to this particular model. So if we want to recap these different steps of evolution, remember we have the dust evolution, removal of millimeter-sized pebbles, where you can either remove the dust by drift or trap the dust and maintain your dust mass. And then on the gas end, you have the viscous or wind-driven evolution that ends up with photoevaporative clear. But it's completely separate from the process that are happening over here. Okay, so if we have these two separate pathways, of course you wonder, like, what causes that? Like, why does one disk get a gap and the other one does not? Well, there is this definition. It's called the pebble isolation mass, which is the minimum core mass that keeps the pebbles trapped outside of its orbit. And it depends a little bit on the location in the disk and the scale height, etc. But we can typically say that it's about 10 to 20 Earth masses at the typical radii of the gaps that we measure. So if we say that the gaps are caused by planets, those planets must be at least the pebble isolation mass, and that means that disk type of cores must have formed really rapidly, essentially in less than 1 million years, because that's when we already see gaps in the disks. Well, using this information, we can now go back to our classification and say something about the planets that form in the different types of disks. So in the compact disks, maybe planets are forming, but they're not massive enough to carve gaps. In the ring disks, you're probably forming you're forming planets, but their minimum mass must be sort of 20 Earth masses. And then for the very large cavities, we have an additional argument that says that, yeah, you need probably super Jovian masses in order to create these really wide cavities. Well, if we now want to check if this is correct with exoplanets, we need to solve essentially two issues. First, as I mentioned in the beginning, planets at wide orbits are rare. So we need to assume that the giant planets that create the gaps migrate inwards. Now we suddenly have a lot of giant planets, so that's good. Second, we need to remember that this exoplanet diagram doesn't include detection and selection biases. This is simply the exoplanets that have been observed. So we can only do comparisons with exoplanet demographic studies, where they looked at the occurrence rates of exoplanets, usually as a function of X, where X can be stellar mass, metallicity, age, etc., etc. So one really interesting statistic is for giant planets, one interesting trend is that the giant planet occurrence increases with stellar mass, well, up to 2 solar masses. After that, it drops down again. But we're kind of limiting ourselves to the 0.1 to 2 solar masses, because that's where we have the numbers for giant planets. And we actually also know from work from the group here that the giant planets around more massive stars have a higher fraction of hydrogen and helium. So they may have accreted their gas more efficiently. But this stellar mass dependence is really interesting because this is something we can compare with our disk demographics. So if we take a look at our big disk survey again, and I now made pie charts of essentially the different classifications for the different stellar mass bins. So the lowest mass stars, as you can see, they have very little gap disks, and the highest mass stars have a very high fraction of gap disks. And that's exactly the same as what we've seen in the exoplanet demographics. And if we now, so we did a bit more thorough Bayesian analysis of this stellar mass dependence. You can look it up in the paper. There's really a correlation between those occurrence rates. And now we can match the two together. So if we look at the occurrence of gap planets, the occurrence of gap disks, we can see that it matches really well with the occurrence of, super Jovian planets in red and then giant planets in blue. That seems to match really well. So it means that, yeah, we probably have enough giant exoplanets to explain the gaps in the disks, but we need to take the stellar mass dependence into account. We need to consider the fact that higher mass stars more commonly have giant planets, and the same goes for the gaps. But overall, higher mass stars are less common, so that's why you don't immediately notice that if you look at the disk statistics. Well, then you may wonder how can you form these giant planets at large radii? And I just want to pose this idea here. It would be good to figure out that this is really happening. It's been shown that at least in protoplanetary disk stage, millimeter dust is very settled. So millimeter grains form a really thin layer in the midplane of the disk. And Villeneuve et al. have shown that enhances the pebble accretion efficiency. You have a very high pebble concentration there. In contrast, if we look at younger disks, so this actually worked also by my PhD student Osmar, he has shown that in disks that are still embedded, that they are actually showing a much more flared distribution of the millimeter dust. So this settling is really something that happens in the first 1 million years. Then, so this will be the way to form the cores. Then the second part is like, how can we then actually accrete enough gas in the gas giants? Well, I have an answer for that too, and that is that the gas disk lifetime is actually closer to 8 million years rather than 3 million years. So this is a study by another student from Victoria, Arnaud, who re-derived this disk lifetime from this disk fraction plot. Basically, we corrected everything with the Gaia measurements, like really checking the membership, and also considered the influence of external UV fields. So we're only including clusters, like regions where the UV field is low, because those are the ones that we can compare consistently with each other. So this implies that you can maybe form gas giant planets by this rapid core growth initially in settled disks, and then you can have a slow gas accretion process because you have this longer disk lifetime. Okay, then another result from the exoplanet demographics is the stellar mass occurrence of Kepler planets, or these close-in super-Earths. These are planets with a period within 50 or sometimes 100 days. So this population of planets decreases with stellar mass. They're really common around M dwarfs and become, pretty rare even around solar mass stars. And the cool thing is, this is something we can relate again to the disk demographics, because if we don't look at the gap disk, but actually the disks that don't have gaps, the ones that are compact, that are drift dominated, that corresponds really well to the Kepler planets with a binary correction. So now we see that the black fraction corresponds directly to the dark gray fractions over here, and the same for the M dwarfs and for the subsolar star. So the compact disk can be linked to the super-Earths, and the giant planets can be linked to the gap disks. So all of this can be summarized in this diagram that we have. So with all the correlations that we have observed in the disk population, we can essentially say that depending on a certain threshold, probably in the disk mass, either you form giant planets. In that case, you have these pressure bumps and you get structured disks. But if no giant planets are formed, or giant planet cores, I should say, the dust pebbles will drift inwards, creating these compact disks where you have really high pebble fluxes in the inner part of the disk that enhance the super Earth formation there. So all of this together seems to be consistent with both the disk and exoplanet demographics. And it would be, this is something that I think we need to implement in new planet formation models. Well, one of the big criticisms that I have received about this scenario is this question, like, do compact disks really exist? Because as I mentioned, we don't know much about them. Most of these disks, we only have upper limits on their size. They are observed with ALMA, but they remain unresolved. But there are a handful of disks that have been observed at very high angular resolution. And it turns out that they are as small, they can be as small as 2 AU in radius, up to like 8 AU in radius. Also, for one of these disks, it was possible to measure the gas disk size, which was much larger than the dust disk size. So these disks are indeed consistent with radial drift. And I have an accepted cycle 9 program with ALMA to measure the disk dust size, like the radius of the disk, for many more of these systems. So hopefully with that, we can increase the number of disks that are compact, where we can derive the information that can be compared then with a super Earth formation model. Another reason why I think compact disk exist comes from a completely different direction. And it was found by Banzatti et al. So he did observations of disks of water vapor in the infrared. So this is the water vapor originates from the very inner part of the disk. Water is mostly in ice form generally, but if icy water pebbles reach essentially the region inside the water snowline, they will evaporate. So Banzatti already proposed this idea that, yeah, compact disks have their icy pebbles drift all the way inwards. So you increase the water vapor. However, if the dust is trapped in dust rings, in dust traps, the water ice will never reach the inner component. And then you get a lower water vapor content. And this is consistent with what was measured. So the water vapor is anti-correlated with the disk dust size. So this is kind of the fact that we see this anti-correlation is also reason to believe that, yeah, they're really compact disks that are drift dominated, and disks where the icy pebbles remain trapped in the outer disk. Okay, but this also suggests that the dust transport in the disk, so where pebbles are drifting and getting trapped, that influences the disk chemistry. And a really interesting consequence of that was found in, well, let's say my favorite disk, Iris 48. This is one that I've studied basically for 10 years now. This is this asymmetric dust trap. You see here the millimeter dust distribution. And we found that many of the complex molecules that are forming in the ices, that the emission originates from the dust trap as well. It's only the CO that is showing more like a ring, like a full gas disk, but all these complex molecules originate from the dust trap. So the dust trap is actually an ice trap. We have one other example of a disk where we found COMS in similar high abundance, that's HT100. Unfortunately, this was observed at really low resolution. So this is the methanol detection. You cannot really see where it originates, but they already proposed the same idea as for Iris 48, that you have your icy pebbles where your complex molecules are frozen out. They drift inwards towards that dust trap. But if that dust trap happens to be warm enough, you can evaporate your ices there and also your complex molecules. And then, so what's a little strange is that only these two disks so far have shown a strong detection of COMS. Well, many other disks have been studied, like people have looked for these complex organic molecules, but haven't found them. But it's actually not so strange if you look at where the dust traps are in all of these famous systems. So here we have the radius of the outer dust ring in protoplanetary disk as a function of stellar luminosity. So the stellar luminosity sets the temperature structure in the disk. And what we find is that Iris-48 and HC100 both have their dust trap in the warm region of the disk, while the majority of protoplanetary disks have their dust trap further out, or the star itself is less bright. So essentially the dust traps are colder. So this can explain why we see COMS in these two disks. And of course, we're going to try to see if the same is true for these other disks, but not in many of the others. So this overall result is essentially suggesting that, yeah, dust transport regulates the ice chemistry. And this has another impact also on the CO in the disk. So CO, the CO snow line is a little bit further out. The idea is that CO in the outer disk is frozen out onto the dust grains because it's outside the snow line. Those dust grains grow to larger sizes, settle to the midplane, drift inwards, and then, you know, maybe they will eventually sublimate their CO again. But the effect of this is that you're removing molecular CO from your outer disk. So you get a CO depletion in the outer disk. And actually, not only CO, but also water and CO2, so essentially all oxygen carriers. This whole process would cause depletion of CO, but also an increase of the elemental C/O ratio. And this process has actually been proven by looking at the CO abundance in disks of different ages. So here we see the CO/H2 abundance. In young disks, it is similar to the ISM ratio of 10 to minus 4. But if we look at the disks in older regions, that ratio drops to 10 to minus 5 or even 10 to the minus 6. So the CO depletion is an evolutionary dust transport effect, which is consistent with that scenario of the trapping. Well, so why do we care so much about this in the context of C/O? Yeah, that is because there is this very famous plot from Karen Oberg from 2011 that says that C/O ratio is this simple step function in the protoplanetary disk. And if we measure the C/O ratio of an exoplanet, we can deduce where it was formed in the disk, because this step function is set by the different snow lines of water, CO2, and CO. And even if a planet ends up at a completely different radius, it will maintain the C/O ratio of where it was formed. So for a long time, this was a very simple idea that could help us to interpret exoplanet atmospheres, which is of course something that JWST is now going to do. However, if we measure C/O ratio in disks, there's a bit of a problem. So there are two main studies of like survey studies of C/O ratios in disks, one in lupus and one in somewhat broader sample. So this was done using the C2H molecule, which I don't want to go into. Essentially what they find for both samples is that, yeah, you have these disks that have a really high C/O ratio, but then you also have a couple where C2H was not detected, implying that the C/O ratio is really low. This is not a continuous distribution. This is really a big jump in sensitivity, or a big jump in abundance, and therefore in the C/O ratio. So there's a bimodal distribution of the C/O ratios. Well, and I thought, well, what if this is again linked to this dust transport and this dust trapping phenomenon, and then depending on where the dust trap is located? So I collected the continuum data of all these disks that were studied with C2H. And here on top, we have the disks that have a non-detection of C2H. As you can see, most of these are compact, but then there's also Iris-48 here. And then these are all the disks that have a C2H detection, so a high C/O ratio. So yeah, we probably want to say like, oh, disks that have rings have a high C/O ratio, and disks that don't have rings have a low C/O ratio. But that Iris-48 is a little weird in that context, right? But it becomes more clear if we look at the location of the CO snow line in each of these disks. Because what you see now is that the disk here on the top with a low C/O ratio, all their dust is located inside the CO snow line. So whatever CO icy pebbles were drifting inwards, they are evaporated again. Well, in the majority of the disks, most of the CO ice remains trapped in the outer part of the disk. So it doesn't replenish the CO in the disk anymore. So this essentially leads to the following idea, that you have either warm disks with a low C/O ratio, because there all the CO is essentially sublimated again, all the icy pebbles have drifted inside the CO snow line, and you have the cold disks, which is the majority. These are the disks that have a dust trap outside the CO snow line, where most of the CO icy pebbles remain. And this means that we no longer have this simple step function of the C/O ratio. You actually need to keep in mind that when a planet forms, it creates a dust trap, icy pebbles get stopped there. So I created this little cartoon, and like there are many, you can talk about many different scenarios here, but the key is in particular, if you have multiple planets in the same system, if that outer planet halts the icy pebbles, that will have consequences for the material that will get accreted onto the inner planet. And then if you add migration on top of that, the whole thing becomes a mess. So I don't, Ravid was telling me, yeah, you should come up with a new, like a sophistication of the Oberg model. I really want to, I haven't figured out how to do it yet. I just want to conclude that, yeah, it's not that simple. There's the consequences of icy pebble drift need to be taken into account as well. And it can essentially mess up this whole idea of the C/O ratio as a tracer of a planet formation location. So with that, I've come to my summary. So there may be two evolutionary pathways for protoplanetary disks, the gapped ones and the compact ones, set by the presence or absence of pressure bumps and therefore giant planets. There's the stellar mass dependence that helps us to link gap disks to giant exoplanet demographics, but also the compact disks to the anti-correlation with the anti-correlation of super Earths with stellar mass. The giant planet formation itself at large orbital radii can probably be explained if you have rapid core growth in settled disks and then slow gas accretion, because we have a lot more time. And finally, the dust transport will have a profound effect on the chemistry, chemical composition of the disk, in particular in these dust traps located just outside of giant planets. So the material that is accreted onto the planet is set by this interplay between pressure bumps and icy pebble drift. So with that, I'm ending my talk and I'm happy to take your questions. Yeah.
So I have a quick question. So if you go to okay, maybe one right. So
yeah.
Here you tell us. Can you tell us in terms of statistics, do we have more cold disks or more warm disks?
We have more warm disks because we have more compact disks.
Right, but that's inconsistent with the statistics that for that
Mm-hmm.
you have this, don't you need to have this planet to separate? And then this is inconsistent with the fact that we don't have so many giant planets, which corresponds.
No. So we have more compact disks, and that is consistent with the fact that we have fewer, we have little giant planets, right? So the fraction of cold disks is small, It's just that in our sample of C over O observations, most of those are cold disk, but that those samples are not well chosen to trace this phenomenon.
Can you translate it and see whether it's
No, you would need well, I've been trying for 2 years to get an ALMA large program to prove that, because you need a sample that is actually representative of a full disk population in order to test that. Yeah.
And then I also have a question. Show the high plot.
Mhm.
Right. So when I'm very bad at statistics, my first thing I would say that it depends a little bit also how you divide your sample.
Yeah.
Which sounds a little bit arbitrary to me, not just here for
Mhm.
but I'm actually more concerned about the ones with the planet.
Yeah. So this one? Yeah.
The boundaries.
I agree, but this is so this is why we did this as a test as well. So we actually fit the stellar mass the occurrence of ring disk and transition disk as from stellar mass. We fit that separately in this way. So this for disks it is consistent, and for giant planets that would be that is essentially this plot. So it's the same thing. Yeah.
Okay, so the last question is
Yeah.
about that. So it's basically you argue
Mhm.
that different kind of process for the dust evolution and the gas.
Yeah.
And kind of you argue that the gas should stay longer, like 8 million.
Yeah.
But then I'm a bit worried because when you show the pie plots, you show that around 1 to 1.5 stellar masses, but this is where we found
Mhm.
giant planets up to 1 Jupiter,
Mhm.
up to Jupiter masses. But if you have the gas staying so long, you would expect to create much more massive planets,
Mhm.
unless you say that the way you stop growing the planet is really to put the gap at, at 1 or 2 Jupiter masses, and then it's a different process, like it's distant or something else. This is really an issue.
Mhm.
If you keep the gas long, you
Yeah.
need to find an explanation why they don't grow beyond this whatever.
Well, this is the stellar mass, right? So this is for
But not here. When show your
this one.
right. So you have this division
Yeah.
0.2 and 1, and then larger than
Uh-huh.
but then you use this kind of statistics to argue and connect it to the disk.
Mhm.
disk
Yeah.
property. But then your gas disk can survive many million years, like 8 million.
Yeah.
Years.
Yeah.
So why would you stop at 1 Jupiter mass? Why wouldn't you have then? Why don't you form
Mhm.
more gas giant planets if the gas disk remains for so long?
Well, so this is not 1 Jupiter mass, right? The red statistic is more than 1, and
Yes,
it goes up to, what is it, 10, 15. And yeah, so well, maybe I don't understand your question. So the protoplanets that we have already found, so in AB Auriga and PDS 70, they are already super Jovian in mass, right? And there's also still gas present in the system. So maybe if all that gas still accretes onto the planet, it's an even more massive super Jovian planet, but it doesn't become a star. It's within sort of 10, like maybe another 10 Jupiter masses or so. So yeah.
I'm worried about this. There is some kind of a threshold.
Mhm. Yeah.
This is an issue also for
Mhm.
transformation. So it's not
Yeah.
But I'm just saying that allowing the gaseous disk
Mhm.
to remain for longer time scale makes it even harder.
Yeah.
If you say, okay, it takes a few million years to
Mhm.
form that plant, and on average, your lifetime is 3 million years, you can
Mhm.
massage it and it makes sense. But 8 million years makes it much harder.
Yeah, well then, so one thing that I didn't really cover that in my talk, but what is also under debate is the viscosity of the disk, right? Like if the viscosity is much lower, then I'm imagining that your accretion efficiency will also go down, and the migration will change in lower viscosity disks. So that may help with that problem. Mhm.
I mean, once you reach higher gas equation, it happens on a very short time scale. We are talking about dynamic. If you have the gas and you have all the time, you would expect to form gas and so much. And it's not
Yeah.
a side topic we are
Mhm.
not so much about that, but I just wonder
Yeah.
whether there is a way to put some limit or to, you know, kind of assess whether this estimate for the gas lifetime.
Yeah. I mean, so one thing about the gas lifetime is that this is an average disk lifetime, right? So there is if I go back to that, no, that's later. I don't remember. Sorry, I don't remember where this plot is. Here. Sorry. So so here we fit a power law through these data points, and well, we end up with something of 8 plus or minus 1. But yeah, if just looking at the plot, this is for an entire disk population. There's a paper by Falsner, which I'm not showing it in here. They also looked a bit at stellar mass dependence of the disk lifetimes. Yeah. So I guess I should add that to the slide. So what I remember from that paper is that indeed the disk lifetime is shorter for higher, more massive stars than for low mass stars, and that would help. Yeah. So this is the average over all the stellar masses. So maybe, sorry, yeah, that I think that answers your question then. But this one would be biased toward low mass stars because there's simply more of them in the IMF. Yeah. No, that's a good point. I should probably emphasize that more because it is really relevant for the gas equation. Yeah.
Then you could have disks have new disks which are inclined. You see then the shadows of.
Yeah.
Have you looked into whether that somehow could be explained by some dynamical interaction between planets?
I haven't, but yeah, there are some studies. Like Shaban Zhu has written a really nice paper about this. So want to stress here that that's inner disk in that case that consists of small grains, right? Like small grains are enough to cast that shadow. So it doesn't really remove my point on the large grains. Misalignment can be simply the result of precession. Like as soon as your planet is so massive that it cuts off the communication essentially between outer and inner disk, your inner disk will precess and get a different orientation. So this is one way of doing that. Yeah.
Never really showed error bars. I wonder if
Yeah, well, well, the error bar that we usually take in the statistics is 10%, because that's a flux calibration error of ALMA. You can consider other errors which are more based on the dust opacity, the assumed temperature. So the assumed temperature is not going to make a major impact, but the dust opacity does, and that's an unknown in that sense. It's depending on the assumed dust opacity, you get a different value. But I would say within half an order of magnitude, you're probably okay. But then if the dust opacity varies from this to this, you're already, that's already not true anymore. So it's, but for this is unfortunately what we do for these statistical studies. In an ideal case, you would analyze each disk independently to derive a more accurate dust mass. Yeah.
about the point that you observe the gaps and you observe 2 planets, I think, that each of some plot there were 2 planets.
Yeah, PDS 70.
Still more, so how clear is basically the statement of saying, okay, we see a gap, it's made by a planet? Because I think I remember papers from like class where they argue you can get this just by hydrodynamic effects, basically. So
Yeah.
Those are great that we have those.
True. So, but I can say that the debate was a lot harder before the discovery of PDS 70 because that was my PhD. But yeah. So this helps, and we can, like, in terms of sensitivity, we're kind of on the limit in many other disks. So the fact that we haven't detected them there doesn't say, like, it doesn't really exclude them. So there's that part. Then there are all these other signatures which we've measured in a lot of the disks that have gaps, at least the large ones. And then finally, I would say the fact that the occurrence of the giant exoplanets matches so well with the occurrence of the gap disks, for me, that is evidence that there are enough giant planets. If something else was causing the gaps, then we have too many giant planets, giant exoplanets, or they must have formed later. You know, you can always come up with other scenarios, but if we assume that the planets form early and in the same way in all systems, then yeah, the other scenarios, the alternative scenarios to create gaps would mismatch with the number of observed giant exoplanets.
Can I just ask
Yeah.
a follow-up question? So, I mean, I don't want to push towards this direction, but I have to ask you.
No, it's okay.
Don't you then think that it would be a solution if you formed your gas, you know, some of the gas giants with some distance stability, form it early enough, and then create this gap, and that's actually kind of consistent with the 10% of you know, not very large.
Yeah, that's fine. Yeah.
So do you have a way to say how we can discriminate among the two?
No. So the thing with disk instability, so this is, from what I can see, is less popular because mostly think of Caitlin Quedder's results, that you need also very efficient cooling in order to make the disk unstable. And if the disk is massive enough to be gravitationally unstable, you would immediately grow to like at least brown dwarfs, or maybe even stars. So this is an argument that I've often heard against gravitational instability. Another thing, so that's the part where I just don't fully understand. Looking at gravitational instability simulations, it looks like the whole disk is destroyed. So then how could you form a planet and then somehow go back to the smooth disk and carve a gap? Because what we're observing is smooth disk with gaps, not a destroyed disk with planets. But maybe that is my lack of understanding.
I think it's different time scales. So
Okay.
This is gravitational unstable, that
Mhm.
is very early time.
Yeah.
And then you would form clamps and you would learn maybe most of the clamps to would start. Then you may be able to have this one object in then create the structure you're looking for.
Yeah.
It just then you
No,
don't
so
have the
that's
chicken
possible.
and the egg.
True. Yeah, so that is possible. I don't really have an argument against that. I guess you could, if you have such a planet, if it's not too massive, you would, I guess you would still expect that it will continue to accrete gas.
So that's
Yeah.
always,
Yeah. And that's always true. Yeah. No, so that is possible. I don't have a way to distinguish. So I think that's if you do, I would love to test it with observation, but from what I have seen, there's no real observational distinction.
Sorry,
Yeah.
How are younger systems surveyed by ALMA, you know, like in Orion or so, where you have really the very first stages of this evolution?
You mean like less than 1 million years?
Yes.
Yeah, well, so you don't need to go to Orion for that. We have those, but those, because they're shorter lived, they're much more rare. There is, maybe 10, I think in Ophiuchus, there's maybe 10 class 0, class 1 systems and 150 class 2. So this becomes small number statistics. Yes. Yeah. But I showed it very briefly. So we have some evidence that these younger disks are more flared. It makes it much harder to say anything about their structure. You cannot analyze the gas disk at all because the envelope is completely dominating the emission there. So we have less information. And even if we focus all my time on the younger disks, we are limited by what we can deduce. And that's simply because of the fact that you have an envelope, the fact that the disk is more flared. It just limits what we can learn from these disks. Yeah. But that would be
So I know from Alma there are some books also looking at estimating the gas mass.
Yes.
I was wondering about comparison with your
Mhm.
estimates and your gas mass.
My dust mass estimates are not different than theirs. So it's the simple, it's, converting a flux to a dust mass. Yeah. And then, yeah.
So you can use that somehow to further constrain your.
The problem is that we don't have a lot of measurements yet of the gas. Like overall, we have seen that the gas masses seem to be very low, but this may be due to this CO depletion because we use CO as a tracer for the gas mass. And if your CO is depleted by a factor of 10 or even 100, yeah, in for example, the Lupus survey, only a third of the disks we have the information, we have CO observations. So this is still, yeah, here we're still, again, very limited in data. There are some ALMA large programs I'm not part of where they're trying to reconcile that. So I'm expecting more gas masses. Yeah.
Question from Zoom.
Yeah.
About the C2 ratio.
Mhm.
Gas transformation. If we have other choices, we break the definition. I mean, degree of the M2 ratio or another isotopic C, but in 3 to 12 ratio.
Well, you would still need to figure out how those molecules, like where they freeze out and how they are transported onto the icy pebbles. So I think that's even less well constrained for like nitrogen bearing molecules, for example. Yeah, like the small molecules tend to have similar, yeah, the COCN are similar, and then CO2 and water are also pretty close to each other. So yeah.
If the nitrogen is easier to observe, what is more difficult to
But well, with ALMA, you mean? Yeah, the problem is that CN is also not a gas, is also a tracer of ionization essentially, and CN is photodissociated in the inner part of the disk, so they become sensitive to many other components. So it's not nearly as well studied as CO, and there is no, as far as I know, there's no tracer. Like the C/O tracer is C2H, like that has been demonstrated with disk chemistry models. If you change the abundance ratio, you get stronger C2H. I don't know if such a tracer is known for the N/O ratio, for example. So it would be interesting to find one. Yeah, but I don't know. Yeah, considering how molecules depend on multiple physical conditions, that may be difficult to really disentangle. Yeah.
Thank you very much.
Thank you.